So we're going to be talking about interval and radius of convergence.
Oppan Gangnam Style.
So for example, when we have the power series of 1 over 1 minus x, which is this right here, we want to know for what values of x will the series converge. For example, when x equals 12, we have the series 12 to the n. And we know that this series diverges according to the divergence test. So when does a series converge?
Dressed in your Friday best and ready to impress. Oh, I like the show. And can I say that you're the
Okay, so what we have here is three possibilities. A series can converge at one point where it is built. Most of the time, x equals 0 or x equals a, wherever it's built, it can converge. Or an interval can converge from negative to infinity, so its interval of convergence is negative to infinity, so all values of x. Or the third possibility is an interval can converge from negative r to r, so a radius of convergence of r. This means that only between these points is when the series will converge. So how do we check to see whether a series converges or not, and where its interval of convergence is? Well, we use the ratio test for absolute convergence. Now, just to help us remember, let's have a quick review of the ratio test. Alright, so what we have here is an example of the ratio test for absolute convergence. We have our series, x to the n. What we do is we take the limit, as n approaches infinity, of the absolute value of x to the n plus 1 all over x to the n. So we have our first term, and then we have the next term in the series. And the whole thing has to be less than 1 for the series to converge, because if you remember, the ratio test says that when the limit is less than 1, it will converge, and when it is greater than 1, it will diverge. So what we're looking for here is when the series is less than 1. So, what we'll do is we'll have the limit as n approaches infinity, and x to the n plus 1 is just x to the n times x all over x to the n, still less than 1, and these will cancel out, so we're left with the limit as n approaches infinity of the absolute value of x less than 1. Well, there's no n left in our terms, so this doesn't matter anymore. So we're left with the absolute value of x less than 1. So the absolute value of x less than 1, or we can say negative 1, and x is greater than negative 1 and less than positive 1. So this is our interval of convergence, but we need to check the endpoints. We always need to remember to check the endpoints, because the test tells us the interval, but it doesn't tell us whether or not the endpoints are included or excluded from the interval. So how do we check the endpoints? Well, we can check the endpoints by plugging them back into the original series. So here's our original series, and we're going to start by checking negative 1. So x equals -1. We're going to plug in -1 into the series, and we all should know that this one is just -1, 1 minus 1 plus 1 minus 1 onto infinity. And we know this series diverges because the sequence of partial sums does not converge. So this one diverges. Now let's check +1. Okay, well this series also diverges because it's the sum of 1 plus 1 plus 1 onto infinity, and we can either say that we know that this series will diverge because the divergence test says that it will. 1 plus 1 added to infinity is obviously going to diverge. So now we know that our interval is from -1 to 1, not including -1 or 1. This means that between these two values, for x, the series x to the n will always converge. And our radius of convergence is simply the distance between these two divided by 2, or from the middle out is 1. So our radius in this case will be 1. Now let's try a quick problem and test for the interval of convergence and the radius of convergence. Okay, so it says find the interval and radius of convergence of the following series, and the series is n cubed times x plus 5 to the n all over 6 to the n. So we're going to start by doing the ratio test for absolute convergence. So the limit as n goes to infinity of the n plus 1 term, so n plus 1 cubed times x plus 5 times to the n plus 1, which is just x plus 5 to the n times x plus 5, all over 6 to the n plus 1, or 6 to the n times 6. And instead of dividing it by this term, we will simply multiply it by the reciprocal. So 6 to the n divided by n cubed times x plus 5 all to the n. And the absolute value of this entire thing has to be less than 1. So now let's cancel out a few terms. These will cancel out, and these will cancel out, leaving us with this. Well, we can combine a few of these terms. We can combine these, and we can take out this. So what we'll have is the absolute value of x plus 5 all over 6 times the limit as n approaches infinity of n plus 1 over n all cubed. And this will all have to be less than 1. Well, as n goes to infinity, since these are both the same power, they will cancel out to 1. So this essentially doesn't matter because it's just going to be this times 1. So we're left with x plus 5 divided by 6 has to be less than 1. Okay, so we have x plus 5 divided by 6 has to be less than 1. The absolute value, so we can say that -1 x plus 5 divided by 6 has to be greater than negative 1 and less than positive 1. Or x plus 5 has to be greater than negative 6 and less than positive 6. So from right here, we can already see that our radius of convergence is just going to be 6. So radius of convergence is 6. Now we will subtract 5 from both sides, so we have x left by itself. We get negative 11. X has to be greater than negative 11 and less than 1. So here's our interval of convergence. Negative 11 and to 1, but we don't know if a negative 11 or 1 are included or excluded, so we need to check the endpoints.
There was a time I used to look into my father's eyes. In a happy home, I was a king, I had a golden throne.
Okay, so what we come up with is the series negative 1 to the n of n cubed, so it's just n cubed alternating, but the divergence test tells us that this will diverge. So we know this series diverges because the limit as n goes to infinity of this term does not equal 0. So that series definitely diverges, and negative 11 is not included. Now we need to check 1. Okay, so what we're left with is the series of n cubed, and this also diverges according to the divergence test, because the limit as n goes to infinity of n cubed, again, does not equal 0. So now we know that 1 is also not included. So we have found that our radius of convergence is 6, and our interval of convergence is negative 11 to 1, with negative 11 and 1 not included in the interval.
Sorry for party rocking.